Here is a demo to our RLO project in which we focused on teaching some combinatorics stuff with different approach than what instructors are already using. And so the reason we started working on this project was that this skills, combinatorics, and discrete math are uh, kind of things that every CS undergrad or CS student has to be equipped with. And because the math behind this, concepts are very different than the math undergrad students used to deal with in their high schools, so these this stuff are a bit tough to be understood. So we wanted to teach them in some more understandable way. Then students can easily, and we hope that the students will easily get the idea behind the stuff way easier than before. So in this regard, we first introduced basic and fundamental rules in combinatorics and counting stuff, which are rule of product and rule of sum and rule of complement. And then we introduced the two important notations, combination and permutations, which are a building block to every counting approach or every counting algorithm. And there are two class of problems which are taught by all instructors around the world, but they are not easy to understand. So we use different approach by helping the students to, memorize the idea behind this kind of stuff more conveniently. And after all, in the end, we introduce the combinatorial reasoning, which is the main goal that, this kind of stuff are taught to students. And combinatorial reasoning is the skill that that everyone who is using this combinatorics has to know, and it is about art of counting without counting, art of proving things without making our hands dirty. And in this regard, we first introduced rule of products, and because this rule of products are a bit tricky to be used, we make an analogy to a logical AND, which is a new way of looking at this rule. And then we introduce and then we visualize this idea behind the rule of product to some Venn diagrams and use some set theory stuff to prove to show that what this rule of product is and what does independency mean, and so how students can get rid of this independency without memorizing anything. And then we give a handy examples and use the screen as something like a board, and then we describe how to do the counting and how to get rid of the independency in this kind of problems while we want to use the rule of product. And again, we do the same thing for the rule of sum. Here we make an analogy, draw an analogy to logical or the union in set theory. So it makes this rule of sum way easier to understand for the students. And again, we visualize this by making an example from set theory and introducing the intersection and helping them to understand how to use this rule of sum. And we show why the intersection doesn't matter when we are using rule of sums. And so with one example, we can again use the set theory stuff to do the counting based on using this rule of sums. And the next next idea is to introduce combination permutation, which are two important notations, and these things are considered as building blocks to every counting problem. And so first off, we introduced the number of ways that we can arrange n different people or n different elements on a line, and then we introduced the factorial, which is an operator which it's commonly used in this area. And then we show what n factorial mean, what is its applications, or uh, in the real life, and where we can have or use n factorial when we face some combinatorial problems. And this is the way that we introduced n factorial. Instead of just writing n factorial is 1 times 2 times 3 times n, we made a code and help students to learn this factorial thing easier. And whenever they see this factorial thing, the first thing that comes to my mind, comes to their mind, is how many numbers or how many possible ways of arranging n people in a line. And then we introduce a combination, which is, regularly taught by showing this formulation, and the students have to memorize this. But here we are given a code, and so which makes memorizing this thing easier for students. So they don't need to learn or memorize this complex, mathematical formulation, but instead they can learn that C of n and R is number of possible ways that we can choose an R players for a team out of a class of n students. And then we draw a handy example to teach what the C of n and R mean. Then we visualize this to help the students know what does choosing 3 people out of 4 people mean. And so we should be explain that the order doesn't matter here, but it does in the permutation. So we again drew another analogy to this permutation notation, which is choosing n people out of r people out of n people and then arranging them in a line, which is congruent with the definition we gave for the n factorial. And again, we make another example by showing that in this permutations, we are interested in choosing r people out of n people, and we want to assign them different roles. And so because this would assert some order on the way that we want to choose this r people, then this permutation thing appears. And then we again give the mathematical formulation and then visualize this and show the students and explain them why the order does matter here and what do we mean by the order, by saying that the order does matter. And here is, the end of introducing the building blocks or the notations. And then we go for binary sequences, which are very useful, tool in CompSci and discrete math. Every student has to know what binary sequences are, and they can translate binary sequences to many different things in CS realm, the realm of CS. And so here we introduce that, and we, teach the students how to do some counting problems in this over this binary sequences. What does C of n and R mean in the realm of binary sequences? And then again, we make an analogy that makes it easier for students to learn how to translate or use C thing or combination thing in binary sequences. And then we present the algorithm, the counting algorithm. And here is a back problem, which is one of the toughest problems that are commonly taught to students in every discrete math course. Here is the ways of putting n piece of candy and choosing them out of r different brands or r different types. And then we again visualize this to a real life application, real life incident when somebody wants to buy 10 candies out of this 4 brands: Jolly Rancher, Snickers, Kit Kat, and M&M. And then we translate this problem to mathematics. X sub Jolly Rancher. This variable means something, and we teach the students what does this X sub Jolly Rancher mean. And then we use this handy example, this tiny example, to generalize it to mathematical formulation, and then we can formulate the back problem. And for teaching them how to do the counting, we again go with a tiny and little example and show them how to use the binary sequences, the idea behind using the counting and combination of stuff in binary sequences to solve this problem. And then we show them why the answer to this problem is related to the combination thing. And so most of and then in the final step, we generalize this handy example to general case and find a closed formula for general n and r. And the way that these concepts are taught in, most of the courses that I reviewed is they just give this closed formula to the students, and they have to memorize this, and it remains vague in their minds. Why this thing is equal to the number of ways of choosing R n candies out of R different types. And the other challenging thing for students to learn is circle permutation, in which it has to be, spotted why circle permutations are different than regular permutation. And here we explain that to students why permutations are important and why they are different than regular permutations. And we clear, after hearing the permutation, everybody would think about n factorial or something like that, but we, you know, disprove this guess. We show that this is not the answer to this question, and again visualize the different cases for a handy example for n equal to 3 to show why n factorial is not answer to this question. And we introduce the rotation thing in the circular lists or rounded lists, and then we use this idea of rotation to disprove this n factorial guess. And it gives the students the required intuition behind why the circle permutations and regular permutations are different. And then we use again this idea of rotation to do the counting and visualize the idea behind that to students to know how to do the counting here. And then they would know why the answer to the circular permutation is n minus 1 factorial, but not n factorial. And then again, we give some, sentences which are, which include the intuition behind this, counting algorithm. And the student can easily remember or memorize this scenario instead of, memorizing just this n minus 1 factorial and be not sure why this is, equal to the answer to this question. And after introducing the counting algorithm and proving that it is equal to n minus 1 factorial, we go with the combinatorial reasoning, which is the most important part and the ultimate goal of this great math courses. And it is the art of counting without counting, or art of proving the combinatorial statements without, having our hands dirty. And here again, we give some famous statements. There are two famous statements that everybody has to know, every CS student has to know. And one way to do the proof is just, writing a formulation, doing the math and proving that these two things are equal. And the other way is to use the notations or codes that we introduced to memorize the combination thing. And then the students can use these notations and codes to describe a proof for this. They can do the reasoning to prove why the right thing is equal to the left thing without doing the math. And it is a very important skill. And then we do the same thing for the other famous and well-known, statement, well-known equation, and then we generalize the idea of combinatorial reasoning here. And this was a demo to our project.